afternoon.
Good afternoon.
There's one more problem I wanted to do for chapter 9 before we move on to chapter 10. So I wanted to do 9-89. All right, so that is, it says, repeat problem 9-88 when the isentropic efficiency of the turbine is 90%. Okay, so we need to know what 988 says. 988 says, a simple ideal Brayton cycle operates with air with minimum and maximum temperatures of 27 degrees Celsius and 727 degrees Celsius. It is designed that the maximum cycle pressure is 2000 kPa and the minimum cycle pressure is 100 kPa. Determine the net work produced per unit mass of air each time the cycle is executed and the cycle's thermal efficiency. Use constant specific heats at room temperature. All right, so we have, and then we have the isentropic efficiency of the turbine is 90%. So we have a ideal Brayton cycle. We have our turbine efficiency. 90% or 0.9. The minimum temperature is 27 degrees Celsius, which is 300 Kelvin. The max is 727, which is 1000 Kelvin. Then they have a max and a min pressure. So the max pressure is 2000 kPa and the min is 100 kPa. And it's constant specific heats. Okay, I think I'm missing anything else. And they want us to find the net work produced per unit mass of air. Okay, so net work so we have kilojoules per kilogram of air they're asking for, and then the thermal efficiency. Schematic. All right, for Brayton cycle, we have a heat exchanger. On the top, we have a compressor. We have our turbine on the right. They're connected. So this is our compressor, turbine. And we have our heat exchanger on the bottom. We're rejecting heat. Okay, so let's draw our path. So we start. And we go into the compressor. So this is state 1, going into the compressor. We come out of the compressor at higher pressure and temperature. And we go to state 2. And then we go to our heat exchanger, where we add heat. And we come out and we go to our turbine, state 3. Okay. Now we expand, dropping the pressure and temperature to 4 here. And then at constant pressure, we reject some heat to get us back to the state 1. All right, so we have our heat exchanger and we're rejecting some heat here. So out of this shaft, we get a network where the compressor has work in. Let's make that a little nicer. The turbine has work out, right? And the network is the work out minus the work in. All right, so where do we want to start with this problem? All right, so what I always suggest in these is we have the schematic, but we're looking for network initially, right? And then thermal efficiency, but I still always would suggest drawing the TS diagram first, okay? All right, if we had some constant pressure lines, we start off at state 1 here. We said we isentropically compress through the compressor, right? So we're gonna go to 2 here. Now we're gonna add heat at this constant pressure to the outlet of the heat exchanger. Now we go through our turbine and we would expand isentropically right there, 4S, and then through our heat exchanger, we go constant pressure back to state 1 because we're rejecting heat. So our entropy decreases just like when we're adding heat. Our entropy increases, right? The turbine, though, it says 4S, so that's because for actual is a little bit to the right because we have isentropic efficiency, so there's a little bit more irreversibilities. In that irreversibility is being generated in the turbine. So we have P2 equal to P3 here, and pressure 1 equal to pressure 4. There's also work here from the compressor, work out from the turbine, and the work net is the work out. Nice work. All right. So where do you want to start if if you have questions on the diagram, where do you want to start with the net work?
COE to get the work in and work out.
Okay, so you want to do, let's do the work net is work out minus work in, okay? So let's do that. So then COE, open system, because now every device, if we put a boundary around any individual device, it's an open system. There's mass flow going in and out, right? And they're all one inlets, one outlets. Okay, so all right, so we have our COE, and if we assume what? So first off, I'm doing kind of a general for any device, and then we said work out and work in we'll do it for, but what can we neglect for any of the individual devices here?
Kinetic and potential energy.
So we can get rid of kinetic and potential.
And then a steady state system.
Yeah, and then we have a steady state, right? So then we're left with since it's only one inlet and one outlet, we're left with this, right? And if we did conservation of mass, in steady state, we have mass flow rate in equals mass flow rate out, because it's just one inlet, one outlet. So the mass leaving that one outlet is equal to the mass entering that one inlet. All right, so that changes our equation to this, okay? And if I actually divide out the mass flow rate, we'll get everything lowercase, and the mass flow rate goes away, and I can move enthalpies over. And I have a generalized conservation energy for any device, any of the devices in the system, the Brayton cycle. All right, so you said work in and work out. So work in is happening from 1 to 2, right? So if we do 1 to 2 now, we have this. We get to cancel heat transfer off, and then if we make it work, work in, that's H2 minus H1. What do I do now from this step?
Get the enthalpies from table 17.
So in this one, we don't have to do it that way, okay? So it said that's if it was variable specific heat. So we have constant specific heat. So with variable specific heats, we got to use that table A17 basically for everything. With constant specific heats, we get to do our assumptions that CP T2 minus T1, right? Your homework will have the Brayton cycle with the opposite. So you'll have to do variable specific heats on the Brayton cycle and constant specific heats on the diesel cycle. It'll be switched, so then you can practice the other method on each. All right, so we have constant specific heats because that's what we were told in the problem. Okay, and now we need, when we go through, we need CP. Do we have T1 or T2?
We have T1.
We have T1. Okay, so we go back up here, and after you draw your TS diagram, now you can kind of make sense of what's being told in the problem sometimes. So they said the minimum temperature, so TS diagram, that's state 1, right? What's the T max?
1,000 Kelvin.
Yeah, and that's state 3 right there, right? And then we have min and max pressure. So min is P1, P4, P2, CP3. Okay. All right, so we have T1, right? But what's
Is the ideal gas law to find T2?
the ideal gas law to find? No. So this is a common mistake I saw in the exam also. So it's an open system device, so you can't use the ideal gas law to relate the mass right here to the mass right here, okay? The mass flow rates are equal, so we can use the conservation of mass that says the mass flow rates are equal, and then use rho VA to relate the mass flow rate at the inlet to the outlet. But the mass, it's not the same mass that's at this location that's at this location at any time. So the ideal gas law where you set the mass is equal does not work that way. Okay, in the closed system, we have the same mass being operated as the piston moves up and down, but it's different as it works its way through the compressor. Okay, so we can't use that to relate the inlet to the outlet. That's where the mass flow rate comes into play, and then that's where you could use rho VA, right? And then you could have a density at the inlet and outlet. That's where you could use ideal gas laws on the density of the gas. But we can't use the ideal gas law directly, okay?
Can we use the isentropic relationships?
So that's the other thing we have, right? From state 1 to state 2, we see right here, the other thing we have is it's isentropic, right? The entropy is being held constant. So we can use that. So we have 1 to 2, it's isentropic, right? So we have isentropic relationships. But this time it's constant specific heat. Okay, last class we did variable. Okay, so on your equation sheet, there's 2 versions for constant specific heats. We can let's be. All right, so we have these 2 equations when it's isentropic and constant specific heats, right? Well, in a closed system, most of the time you would be using this version right here. So if we were doing the diesel cycle where we knew compression ratios, that's in its constant specific heats, that's the version we'd use. In a Brayton cycle, we know the pressures, right? So we use this first one. Okay. So in this case, we have temperature one in absolute because we're multiplying it times something. We have P2 over P1, which is also the pressure ratio. So if we wanted to solve for the pressure ratio, it's P2 over P1, right? And we have 2,000 divided by 100, right? So it'd be a 20. Pressure ratio if we wanted to solve pressure ratios. But if we already know P1 and P2, so we don't have to solve for the pressure ratio directly. But some of these problems, that's all they'll give you, and not the actual pressures at state 1, 2, 3, 4. All right, so we have P2, P1, our ratio of specific heats. This is where it's constant specific heats at room temperature, they told us, so we can use table A2A, and we get K is equal to 1.4, and we can get our CP, 1.005 kilojoules per kilogram Kelvin. All right, so then we get T2, right? And T2 is 706.1 Kelvin. We go back up. So now we have T2 and CP. So we can get our work in. Let me calculate that real fast. I don't have the value for that. So we get 408.1 kilojoules per kilogram. So that means we come back way up here and we have our work in. So we need our work out. So what do we do for that?
Look at 3 to 4.
3 to 4. Yep. So similar. So now we go 3 to 4. And again, I'll start with that generalized conservation energy for an open system with one inlet, one outlet. And it's steady state. So, and this one, it's a turbine. We have an isentropic efficiency for something that's isentropic or has an isentropic efficiency. It's adiabatic, right? So then we have work out is H3 minus H4, okay? We can put in our CP, T3 minus T4. Again, because it's ideal gas, constant, specific heats. All right. So if we have CP, we go through and see what we have. We said we have T3 because they gave us T max. How do we get T4?
Is it using the same process, the isentropic relationship?
Okay, so we can use the isentropic relationship to get 4S or 4 actual.
It would give us TS. So is there a way to get actual though? Then S isn't constant.
Right. So let's go back up to our TS diagram, right? So actual is this point, right? And the isentropic, using the isentropic relationship, is that point. Okay, so we can get, from the isentropic relationship, we can get 4S. So let me label what we have down here. And I left it off on port. This is actual. So that's T4 actual right here. And this is the actual right there. T4 actual. More obvious. All right. That wasn't that much better. All right. So that would be, with the isentropic, we can get 3 to 4S. It's isentropic. All right, and if we rearrange for T4, this ends up being T4S, right? So we have T3. They gave us P4 and P3, which ends up just being 1 over the pressure ratio. And we have K, because we already looked it up, okay? So we can solve. So we get T4S is 424.9 Kelvin. All right, so that gets us T4S. We're still looking for the T4 actual. So how can we go from T4S and get our T4 actual? What do we have given in this problem?
We have
for the
our
turbine?
topic efficiency.
Yeah, the isentropic efficiency, okay? So it tells us about how far away from being an isentropic turbine it is. If the isentropic efficiency is 100%, the turbine is isentropic and 4S is equal to 4 actual, okay? But we're 0.9, so we got to utilize that, okay? All right, so isentropic efficiency. If for a turbine, that's the actual work over the isentropic work, okay? Because the isentropic, when there's no irreversibilities, and would be reversible and adiabatic, it's isentropic, you would get the most work out of the turbine. The actual is adiabatic, but there's irreversibility, so you get less out of that turbine, okay? If we divide the mass flow rate out, we can get lowercase w. We put in enthalpies, we would get this. So if we have variable specific heats, we'd have to use something here. But we have CP, we have our constant specific heats. So we have this, CP's cancel. So we just have T3 minus T4 actual over T3 minus T4S. So if we look at this, we were given the isentropic efficiency. We were given T3, our max temperature, and we solved for the isentropic temperature at the outlet. So we have T4S. So the only unknown in this equation is T4 actual, okay? So then we can solve. We get 482.4 Kelvin. Okay, so now we go back up and we have enough to solve for our workout. Can you calculate it? So we have 520.2 kilojoules per kilogram. And we go way up, all the way to the top. So we can get our net work, just work out minus work in. And that's going to be equal to 112.1 kilojoules per kilogram. And that's the answer to the first part, okay? The second part, any questions first?
I'm confused on the units. If you were to multiply by the mass flow rate, that would give you power?
Yep.
Okay.
Yeah, so you would have, let's say, kilojoules per second, which is kilograms per second that you're multiplying it, then it will give you kilojoules per second. It's kilowatts, right? So the mass flow rate ends up kind of being a scalar, like your states on your diagram stay fixed, whether it's a small system or a large system, state 1, 2, 3. That's just dependent upon your properties. Mass flow rate so it scales it to be a bigger device or smaller device. All right, so now we have, any other questions? Now we have the thermal efficiency, right? Oh, it's still a heat engine, okay, like if we went all the way up to our diagram or schematic, and if we put our boundary around this whole thing, we would see the heat in, heat out, work net is all leaving us. This is everything inside this boundary I just drew is that heat engine, that center part of the schematic in chapter 6. All right, so we have work net, overheat in, work net was work out minus work in, over Q in. We could have also done, well, I'll say that. We have work, so we already have work net, right? So we need heat in, right? So where do we get the heat in from? How do we solve for that?
2 to 3.
Yeah, so we have 2 to 3 is our heat exchanger. We're adding heat, raising the temperature while pressure is staying constant. Right? All right, so we have process 2 to 3. There's no work. So heat in is H3 minus H2. Which is again CP delta T because we have constant specific heats. And it's an ideal gas. All right. So we have the CP, we already looked it up. We have T2, we already did the isentropic relationships to get T2, and T3 was given to us, okay? So then we have our heat in, which is 295.4 kilojoules per kilogram. So we come here, we have our heat in then. So we have work net, we have our heat in. So we can solve for thermal efficiency. So we get 0.375, or sorry, 0.379, or 37.9%. Questions on that?
How do you know exactly what is like in and what's out in terms of entropy or enthalpy?
Enthalpy. So this would be, in this case, out is, let's go back up. Come on, load up, computer. My computer's being slow. There, okay. All right, so we have on the heat exchanger that we're adding heat. This is out right here. And this is in, right? Okay. And then the subscript on these, that means it's a heat in. So that already tells us the direction. So the negative sign can go away when you do that subscript, right? So like we did for work in, we had enthalpy out, right, was H2. So this would have been negative work is H2 minus H1. But I changed that subscript to work in, which gives me H2 minus H1 without the negative, because that basically that in tells us the direction of the work. I know the enthalpy at state 2 is going to be higher than 1 because we're putting in work. Okay. Or you can leave it as a negative, solve, if you're not sure, you can get your negative here, and then say that work in is the positive value of it. Any questions?
Could you have also used the, they give like a thermal efficiency in the book for a Brayton cycle? I think someone just commented that.
Yeah. In this case, I think you can, but it only works when you keep this constant specific heat at room temperature, and only with, again, constant specific heats. So that equation does not hold true if it's variable specific heats, and if you're taking a CP that's different for the different processes. Let's say you took the CP average from T1 to T2, the CP average from 2 to 3, the CP average from 3 to 4, and so forth. Then you wouldn't, that equation doesn't hold, it doesn't approximate that. So that equation is only for the assumptions that go along with that equation.
Okay.
Okay, so variable, like we did, variable specific heats of the diesel cycle last class, there's a efficiency for the diesel cycle in the book, but it doesn't hold true for variable specific heats. Okay, so it wouldn't have been a correct analysis. All right, the other thing I wanted to ask about is we could have solved for work net one other way here. Like we solved it with work out minus work in. How else could we have solved for that?
Q in minus Q out.
Yeah, so and that's from the COE and the whole system. Okay. So if we look all the way back up on our schematic, I drew this boundary around the whole system. Well, the only thing leaving the system, because this work out of the turbine is some of that's going back to the compressor. The network is leaving. You have your heat in, you have your heat out. So work net is equal to heat in minus heat out, just like on our heat engine schematic in chapter 6. Same if you did the your boundary on here, right? Well, work out minus work in is work net. So Q in minus Q out is equal to work net. And if we did it that way, we would have had one COE to solve for Q in, one to solve for Q out. And so we would only have to do the COE twice, okay? So a lot of times that's the quicker way because it ends up being a little less numbers that you have to get. They're both directions are correct, right? You'll get the same number if you solve for work out minus work in or Q in minus Q out. And you had to get all the states. You'd have to still get state 2 information and state 4 information. Okay, so, but it does typically save you a one step of COE. Okay. Because in the thermal efficiency, you always need this Q in, so you would need to get the Q in no matter what. Okay.
And you can do that with any type of process, or does it have to be like constant specific heat?
No, this is how to use any assumptions to solve for this, other than a boundary. And I didn't put in any properties, right? I didn't start put in delta H and CP delta D to CP delta T yet in this equation. Okay, where the one that